Last time we talked about the completeness of the trigonometric functions. And let's review this. It's a very important concept that basically our interest from the very beginning will be functions or continuous time signals that are square integrable on some finite interval from A to B. And we can think of this as a period of some periodic function, okay? Now, completeness means what? In our context here, completeness is a word that actually we will see it in this lecture in another, like sort of with another meaning. Completeness here means basically that the sines and cosines are a basis, that you can take any L2 function and you can express it as a linear combination of those sines and cosines, okay? And completeness like sort of implies that, and this is the idea that we used in the proof, that if there is a function that is orthogonal to the cosines, including basically the constant signal and the sines, then it must be the case that this function is equal to 0 almost everywhere. Okay, so again, if I gave like sort of a trivial example that if you are in the three-dimensional space and I gave you those three canonical basis vectors, why actually those are basis vectors and they span the three-dimensional space? It's because if you want to find a vector that is orthogonal to each single one of these, the only vector will be the all zero vector. Okay, so for functions, because orthogonality is defined in terms of an integral, right? So basically the inner product of two functions, x1 and x2, will be the integral from a to b x1 of t, x2 conjugate of t dt. And basically orthogonality, so if this is equal to 0, we say that basically the two functions are orthogonal to one another. Now orthogonality here is defined not with the sum but with an integral, and integrals are insensitive to whatever happens on a set of measure 0. And so the conclusion here, if we have a function that is orthogonal to all those guys, the conclusion is not that the function is exactly 0 everywhere, but that it is 0 almost everywhere, because if basically this function is non-zero on a set of measure 0, still the integral will be equal to 0, okay? So this is the idea, and basically the proof is a proof by contradiction. By contradiction, which means that we will assume the existence of an x of t that is not equal to 0 almost everywhere, and that is orthogonal to all the sines and cosines. And then we will show that basically this leads to a contradiction, and hence basically if x of t is orthogonal to the sines and cosines, it must be equal to 0 almost everywhere. Okay, so the proof outline, as we did it last time, that we started with x of t, L2 function, L2 AB function, so it is a square integrable from A to B, and we assume that it is continuous. So basically the proof is like two parts. We did one part and the other part is in the notes. That to make life like easy, like we need x of t also to be continuous. And then if it is not continuous, then there is a trick actually to obtain a continuous function from it. So basically, if you have an L2 function that is not continuous, if you integrate it, then you get a continuous function. And so that's the trick actually to complete the proof. But we focused on the case in which x of t is continuous and it is positive at some point. Okay, so there is between a and b, there is some t0 at which basically x of t0 is positive. Okay, so our starting point is that there is an L2 AB signal that is continuous and that is orthogonal to all sines and cosines. Okay, now if you have this function and it is not positive at some point, it is negative, just multiply it by -1, because multiplying, if a function is orthogonal to all sines and cosines, then its negative is also is also orthogonal to all sines and cosines. Okay, so this is without the loss of generality. We'll assume that the function is positive at a point, and because the function is continuous, then it is strictly positive. Okay, on a neighborhood of that point. So basically, you can find some delta such that on t0 minus delta to t0 plus delta, the function is greater than half its value at t node, and if x of t node is positive, then this thing is strictly greater than 0. Okay. Then we constructed a function which is alpha of t. Okay, so alpha of t is a function that basically is a continuous function, and that is composed of sines and cosines. So, and if you raise it to the power n, you will get basically things that look like those functions here, the cosines and sines here. Okay, so this was a function, and remember, it was basically designed so that on the interval in which x of t is strictly greater than x of t0 over 2, this function was greater than 1, and then elsewhere it was less than 1, but its magnitude was basic, so it never reaches minus 1. And basically what we did is that the contradiction was basically to first use the assumption. So the assumption is that x of t is orthogonal to all sines and cosines. So alpha of t to the power n is a combination of those sines and cosines. So if by assumption x of t is orthogonal to all those guys, then this integral is 0 for every n, for every small n, and so basically if you take the limit as small n goes to 0, this will be like the limit of the all 0 sequence, which will be 0. So this is one way. The other way is actually to try to evaluate this limit. And to evaluate this limit, the trick was to divide it into two integrals. Okay, so we'll take this integration from a to b, divide it into an integration from t0 minus delta to t0 plus delta, and then an integration on ab, basically excluding this interval here. And using the dominated convergence theorem, we proved that basically this other integral also, if you take the limit as n goes to 0, it goes to 0. Okay, so this is not helping, the contradiction that we are hunting for. But fortunately, we proved that basically this integral here, we used basically the continuity of, the functions, the extreme value theorem. We showed that basically this integral is lower bounded. It's lower bounded by by some positive number times a number that is greater than 1 and that is raised to the power small n. So basically, this number is getting large without any bound. Okay, so basically the limit is actually infinity. Infinity plus 0 is infinity, but this contradicts this fact here that, based on our assumption that, that the function is orthogonal to all sines and cosines, this limit should have been equal to 0. So something does not make sense. And this thing that does not make sense is our assumption that there is a function that is orthogonal to all sines and cosines. That there is an L2AB function, a function that is a square integrable from a to b, that is orthogonal to all sines and cosines. Again, the argument needs to be extended, so it's not the complete argument. You need actually to reach the final conclusion and deny the existence of an L2AB function that is, that is orthogonal to all sines and cosines. You need also to consider x of t that is not continuous. So the argument can be extended, and the conclusion now is this very important thing, that if you have an L2 function, AB, so again, this means that the integral AB x of t squared dt, that this thing here is less than infinity, it's finite. The only function that is orthogonal to basically is a function that is 0 almost everywhere. Okay, and now, this business of completeness, you may think that is like, it is not important, but in fact, as we will see, like the Fourier series depends a lot on basically this notion of completeness, as we will see. Okay, so let's go to the Fourier series, and I will do it as a general series. Okay, so not just sines and cosines. I will assume that we have some function which is x of t, and it's defined on AB, and it is L2, okay? And we want to approximate this function as a linear combination of basically of orthogonal functions, of big N orthogonal functions, okay? So we have a function x of t, and we want to approximate this function with something which I will call x hat sub n of t. Okay, so it's x hat. The hat means that this is an approximation. It is not x of t. It is an approximation to x of t. And this approximation, it uses basically, let's say, L from 1 to big N functions phi L of t. And those functions are basically an orthogonal family of functions. Orthogonal family of functions means the following. It means that if you find the inner product of phi L of t, phi m of t dt, and conjugate, generally speaking, those will be complex valued, then this is, if the two indices are the same, if L is equal to m, you will get the energy. You will get the energy of basically the function phi L of t, and so let's call this EL, and we'll assume that EL is a positive real number. If L is not equal to m, then this is 0, which means that we have an orthogonal basis, okay? Sorry, orthogonal family of functions, okay? Now the sines and cosines are basically an example, but here I will do the formulation using like general orthogonal families, because there are several of these, not just the sines and cosines. You know, you can use things like wavelet functions, Legendre polynomials, and so on. So there are so many families like this. Okay, it's not only the sines and cosines. Okay, so we will have functions again that are orthogonal to one another, so the inner product of one function and another one different from it will give you 0, but if these two indices are the same, you get the energy, and the energy is some positive number, some positive finite number. Okay, so we will approximate our function x of t by basically big N of those guys, and each one of them is weighted by some coefficient, which I will call alpha L. Okay, so this is the function. It's an L2AB function, and this is its approximation, again constructed by using a known and agreed upon family of orthogonal functions. Okay, I do not here insist on orthonormality. So, you know, so basically you can choose your functions to be orthonormal. So orthonormal means that you also, in addition to orthogonality, you choose the energy of each one of those phi's to be equal to 1. So EL is 1 for every L. Okay, but for example, the Fourier series with sines and cosines is not orthonormal. Not only also the complex Fourier series. So that's the reason I'm not insisting on orthonormality. I just want orthogonality. Okay, and in general, I'm allowing every one of those guys to have a different energy from the others. Okay, orthonormality will be the special case in which the energy of each phi is exactly equal to 1. And we will basically emphasize the role of n here by this n, because if you think about it, you studied the Fourier series before, and like the Fourier series, the summation is infinite. It's an infinite sum. We take a signal that is periodic, and typically it is represented using an infinite sum of sines and cosines. So so basically, you know, we will fix n initially, and then we will investigate what happens if this big N is pushed towards higher and higher values. Okay, So this is now the business. So we are trying to like basically derive the Fourier series as by setting up an optimization problem. So this optimization problem will be the following. What is the best approximation of x of t that looks like this? That looks like a linear combination of some functions that basically that constitute an orthogonal family of functions. Okay, and then when you talk about optimal or best, then you need to define in what sense. Okay, so so we have those functions again, and they are basically an orthogonal family, and we are trying now to find the coefficients. So the functions are assumed to be known. So you choose the family. This family is well known. So the sines and cosines, for example. So your objective now is to obtain those coefficients such that your approximation is as good as it can be in some sense. Okay, now those coefficients can be a proxy for the function, right? So basically what I'm talking about now may be abstract, but it is the essence of compression. When you compress a signal like an audio signal or a video signal or any multidimensional signal, sometimes we do compression like this. You take the signal and you express it using some functions, not necessarily orthogonal, but in some applications you use orthogonal families like what I am doing in this lecture. And then the coefficients that you obtain basically can be a representative for the signal. You can basically use them in place of the signal. Okay, so for example, if you want to store the signal in a compressed form, you can basically store those coefficients. Okay, so those coefficients will be a proxy for the signal, and you can, if you know the coefficients, you can construct an approximation of the signal by basically taking each coefficient, multiplying it by the respective phi function, and then adding. Okay, so what I'm talking about here again, if you're interested, this is the essence of lossy compression, of lossy data compression. Now, how do we obtain those coefficients? The difference between x of t and x hat n of t is an error. Think of it as an approximation error. Like it's the difference between the true function or the true continuous time signal x of t and its approximation. Okay. Now, to set up an optimization problem, you need a functional of the error, right? Because this is the error at t. Okay, and so this error is basically we want this error somehow to be represented over the interval from A to B. Okay, and so we typically do this. We can obtain those guys by minimizing the mean squared error. So the mean squared error means that you take the error at time t. Okay, so this is the error between the signal itself and its approximation, and don't forget that this approximation has a certain form. It is a linear combination. It is a linear combination of those known phi functions. And what we do is that we take the square, okay, or the magnitude squared, okay, because those guys can be complex valued in the general case. So we take the magnitude squared, okay, which sort of tells you that, we don't care about, we care just about the magnitude of the error. And then you sort of integrate, right, between A and B. So this will give you a number. It will give you a non-negative number. So this will be the mean squared error. And so we can have our optimization problem as obtain those alphas such that the mean squared error is minimized. Okay, and this is exactly what we will do here in this lecture. Okay, so so the mean squared error, you can think of it as just the L2 norm squared of the error. Of course, this is not the only function. This is not the only plausible function of the error that you can think of. You may think of just finding the alphas to minimize the mean absolute error, in which here you integrate basically the magnitude of the error, not the magnitude squared of the error, from A to B. I am calling it a functional because it takes a function, so you can think of the error E of t as this error. Okay, so it is a function, right? Because this is defined for t from A to B, and it spits out a number, just a number, right? So it is, I'm calling this thing a functional, again, because it's like this, you give it what? You give it the error at every t from A to B, but it sort of, combines all those errors and give you just a single number. Okay, so that's the reason I'm saying that it is a function. Okay, you can do mean absolute error. You can do basically minimax optimization, which you minimize the maximum error. Okay, you minimize the maximum error. So you can do these things, and like in modern signal processing, we use L1 norm minimization a lot. Okay, if you know about like sparse signal processing and so forth. But classically, we focus on mean squared error because it's like the most tractable mathematically, and you can have closed form expressions for your solution. I will give you a formula for basically the optimal coefficients, those alphas. The other guys, basically the alphas, can be computed numerically in an efficient way, but like you don't have a closed form for them and so on. Okay, so classically people started by the mean squared error. Again, it's the most mathematically tractable, basically functional of error that can be handled. Okay, so so now, I mean, let's recap basically what we are talking about. So we have a function Lx of t. It's not any function walking in the street. There are so many weird functions, and so we focus just on L2AB functions that are square integrable from basically on the interval from A to B. We want to construct an approximation, and this approximation will take a very specific form. We choose an orthogonal family of functions. Okay, and then we take big N of them, and then we approximate our function x by basically having some weighted combination of those guys, and this will be our approximation. Okay, and this will be our, so those guys are basically an orthogonal family. Orthogonal family means that basically phi n is orthogonal to phi m for every n that is not equal to m, which means that the inner product is phi n of t, phi m conjugate of t is dt. This is 0. Yeah. It's basically mean squared error. Its solution is a projection. Yes. It will be the projection. And this, we will basically drive this, and it's a general basically phenomenon, by the way, regardless of how, so yes, those alphas will be the projection of the x's on the, once you minimize the mean square error, your solution is the projection of, those, this function x of t on basically those functions here. Again, we just use an orthogonal family, not orthonormal, because actually the Fourier functions, the sines and cosines are not designed, are not, the way they appear in the Fourier series are not, they are not orthonormal, and we allow actually that the energy of each guy is different from the other. So basically, phi n t squared, this energy is En, and it's just a number that is living between 0 and infinity. Okay, and the difference between these two guys, the difference is an error, and what we will do is that we will minimize basically the mean squared error. Okay, so this is mean squared error squared dt. We will minimize this guy here. Okay. The optimal coefficients. Okay, so so now we are setting up an optimization problem, and basically in a course on optimization or some course like, sort of more advanced than what we are doing, we will rewrite the mean squared error in a compact form using vectors, and we will do something called differentiation with respect to vectors, so that we can very quickly get the solution. But here, I will just, do things, do things. I will not hide any details. I will just, tell you the story, in its sort of basic form, which is important actually to know. Because sometimes, like, when you do things in a compact form, like, you forget about actually what you are doing. Okay, so let's here expand our mean squared error and write it explicitly in terms of those parameters, those optimization variables, which are the alphas. Okay, so this is J. This is, the mean, this is basically the error, the magnitude of the error square, and this is basically the x head. This is the approximation. Okay, and so first order of business is to find the magnitude square, and you just take this guy here, you take this guy, and you multiply it by complex conjugate, right? So the magnitude square of a complex quantity is the quantity multiplied by its complex conjugate, and so you get how many terms? 4 terms, right? Because you have this and this and this and this, so it's like a bracket with 2 terms, another bracket with 2 terms, then we get 4 terms. The function multiplied by its conjugate, that's the magnitude of x of t squared, and then basically we have basically this summation multiplied by x of t, and we have this x conjugate of t multiplied by the other summation, and then we have the 2 summations multiplied together. Okay, and now we are integrating this thing, so we will basically integrate. So we take this formula here, and we integrate every one of those terms from a to b. Now here's the nice thing. Which is that starting our problem with a finite number of terms, big N, you don't even need to justify basically interchanging the order of summation and integration, because integrals are linear. And so if you are integrating, if you are integrating a term like this, integral summation n from 1 to n, this is summation n from 1 to n of the integral. I mean, because integration is linear. Okay, Riemann integrals are linear, Lebesgue integrals are linear. Okay, and the problem is, like, if you started with what we do in engineering, typically, like, you start with the infinite sum, then actually this interchange is not always warranted, right? It may not be correct. But here again, there is no problem in interchanging the integration and the sum, because the summation is finite. So you will basically integrate each one of those guys, and you can push the integral inside the sums because we have finite sums. Okay, and so our integrals will. So this guy here will be the integral of the magnitude squared of the function. That's the energy of the function itself. Okay, that's the energy of the function itself. And then what happens if you integrate? What happens if you integrate this guy, or if you integrate this guy? Let's focus on this guy. So we will integrate from a to b, summation n from 1 to big N, alpha n x conjugate of t phi n of a phi n of t dt. Again, because we have a finite number of terms, we can basically swap. So this is minus n from 1 to n, and then we have alpha n, and then we have integral from a to b x conjugate of t phi n of t dt. Okay, and this thing here I will call beta n conjugate. So beta n conjugate is basically this integral, and beta n itself will be the integral from a to b x of t phi n conjugate of t dt. So beta n, x is not conjugated, phi is conjugated, beta n conjugate, x is conjugated, phi is not conjugated. Okay? And so basically, when you integrate those terms, you will get one summation will be summation n from 1 to n alpha n conjugate beta n. The other will be minus n from 1 to big N alpha n beta n conjugate. Again, beta is an integral involving x and phi n. This is beta n, and this is beta n conjugate. And then here comes the nice thing. What happens when you integrate this term here from a to b? Now, when you integrate this term from a to b, now you can make use of orthogonality, right? So when integrated, And again, we have finite number of terms, so we can move the integral inside the summation, and this will be summation n from 1 to big N, summation m from 1 to big N, alpha n conjugate, alpha m, and then integral a to b, phi n conjugate of t, phi m of t dt. Now, you can exploit orthogonality, because if n and m are different, we are working with an orthogonal family, so this integral will be exactly 0. If n and m are the same, then basically this integral will give you En, which is the energy of the continuous time signal phi n of t. So basically our double integral will collapse into a single integral, because we only have non-zero terms when these two indices are equal to one another. Small n equals small m equals 1, small n equals small n equals 2, and so forth. In this case, so we'll get n from 1 to n, and then we'll get alpha n conjugate alpha n, so it's magnitude alpha n squared, and then we will get En, which is the energy of En. Otherwise, the terms, the big N squared minus big N terms in which the two indices are different, all those terms will be 0, because we are using an orthogonal family of functions. Okay, so orthogonality basically gives you, basically this nice simplification, and yeah, so you just get this summation here, and now this is your mean squared error. So the mean squared error becomes basically, it's a term that you do not control. This is the energy of x of t, and then we have our coefficients, the alphas. The betas are given. So the beta, again, beta n, by definition, it's the integral from a to b, x of t, phi n conjugate of t dt. Okay, and En is basically the integral a to b and phi n of t squared, magnitude squared dt, like this. Okay, I just want to highlight something, which is like in modern signal processing, like in many cases we do not insist on having orthogonal family of functions, or even functions that are linearly independent. Sometimes, or actually many times, we use basically over complete families of functions. So basically families that involve basically functions that are linearly dependent. So you can take one of them and write it as a linear combination of others. Okay, so we use things called frames. This, we will not see this in this course, right? But I mean, it's just important to highlight that the classical way of using orthogonal families is not the only thing that is being used. It makes the math easy, especially when coupled with minimum mean squared error minimization, but it's not sort of the best way to go in some applications. And sometimes, again, you don't just use phis that are linearly independent. You can use many phis that are actually sort of redundant, so basically they are linearly dependent on one another. Okay, but this is a different story from what we are doing here. We are here basically with orthogonal families. Okay, now like QAM, what do you mean by QAM? Quadrature amplitude modulation in communications? No. And I'm talking about something called frames. You can look it up. Frames. Oh, okay. Okay. So now our variables are generally speaking so those alphas, generally speaking, they will be complex numbers. Okay, and so basically let's write our optimization variables explicitly in terms of their real and imaginary parts. Again, so if, for example, I teach another course called the mathematical methods, and in that course, actually, we do not do this at all. If you see optimization variables that are complex valued, you just deal with them in their complex format. Okay, but it's not bad actually to see how things like proceed in slow motion. So our function depends on the alphas, and the alphas are complex coefficients, so they have real parts and imaginary parts, and those betas also can be written as real parts and imaginary parts. Okay, and so you can basically rewrite everything here explicitly using the real part of alpha n, imaginary part of alpha n, and the same for beta n. So for example, this magnitude alpha n squared can be written as the real part squared plus the imaginary part squared, and then we can take these two guys and combine them, and this will give us basically this expression here. So it will be like 2 multiplied by the real parts of alphas and betas multiplied together, and plus 2 the imaginary parts multiplied together. So here is our objective function. So this is our MSE, and it is written now in terms of the real and imaginary parts of the alphas, our optimization variables. Okay, so how do we find? So we want to optimize. So what is the minimum of J? How many optimization variables do we have? Okay, so our optimization variables are the real and imaginary parts of alpha n. So basically we are minimizing over alpha n r. So these are the real parts, n from 1 to big N, and also we have those guys. Okay, so we have 2n, 2 big N real valued optimization variables. Okay, now our function is quadratic, right? If you see our function, you will find that those guys are squared, and here they are linear, and this is just a constant that does not depend on the optimization variables. Our function is actually quadratic, and it's twice differentiable, and basically it is a C2 function. Okay, so this is actually a C2 convex function. It's a C2 convex function. Okay, the word convex will not, if you know it, it's okay. If you don't, I mean, it's not important for us here. Now, how do we minimize this function? So basically, that was the business of the last tutorial session. So a necessary condition for optimality is that the gradient vector is equal to the all zero vector. Okay, so this is what we'll do. So we will obtain our gradient vector, and the gradient vector is the vector of the partial derivatives of the objective function with respect to the optimization variables. Okay, and so the first thing is to compute basically the partial derivatives of the mean squared error with respect to the real and imaginary parts of those optimization, of alpha n, the optimization variables that we are interested in. Okay, and so for example, if you partially differentiate with respect to alpha v comma r, okay, so let's see, this is a constant. So when you do partial differentiation, this will give you 0, right? So basically the derivative of this integral e to b x of t squared dt with respect to alpha vr, this will be 0 because this is a constant that does not depend on any of the optimization variables. Now let's look at this summation here. So this is a summation. This is basically a linear combination of those alphas, and basically there will be a term. So there will be a term in this summation that is equal to minus 2 alpha vr beta vr. Okay, and there will be other alphas, the other terms of the sum, but we are doing partial differentiation. So basically the other alphas, when you differentiate with respect to one of them, the others are treated as constants, and so basically this will give you minus 2 beta vr. Okay, now what about differentiating this term here? Now this depends only on the imaginary parts of the alphas, and so when you partially differentiate with respect to the real part of alpha v, then basically this guy here will give you zeros, and then finally this term here will give you 2 alpha vr ev. Again, because this is basically a summation of terms, one of those terms will be alpha vr squared ev. And so its a partial derivative with respect to alpha vr will be 2 alpha vr ev. Okay, and this part does not depend on the real parts of the optimization variables alpha n, and so the partial derivative will be 0, and so we get this. This is our partial derivative, and we equate to 0 because a necessary condition for optimality will be that you equate all the partial derivatives to 0, and this will give us this expression here, that the real part is 1 over EV multiplied by beta V comma R. And our optimization variables are not just the real parts, they are also the imaginary parts. We have a total of 2n real valued optimization parameters, and so we take, we do the same with respect to the imaginary parts, and this will be the partial derivative. We equate to 0, and this will be the formula. Okay, so those are basically the real and imaginary parts. Are we done? Then you need to do a check, and the check is basically to make sure that what you get, when you equate the gradient vector to 0, you want to make sure that actually you get the minimum, and in this case you need to check the Hessian matrix. And if you check the Hessian matrix, it's there. I will not go through the details, but you will find that at the stationary points, at which the gradient vector is all 0, basically the Hessian matrix is strictly positive, and this is sufficient for optimality. Okay, so the check is here. So basically you can compute the Hessian matrix. It is a 2n by 2n matrix, and in our case here, basically the Hessian matrix will be a diagonal matrix, and on its main diagonal will be positive elements, and so the Hessian matrix is actually positive definite, and this makes your solution. So you are sure basically that your solution, when you equate the gradient vector to 0, that basically this is the minimizer of J. It is actually the unique minimizer because, again, our function is actually convex. It's a strictly convex function, but again, this is beyond this course. Okay. So you have a formula for the optimal real part, a formula for the optimal imaginary part. You can combine them together, and this is what you get. This is the minimizer of the mean squared error. The optimal coefficient. So someone said that it's the projection. So it is. So basically the optimal coefficient alpha n. Okay, and with a hat means that this is this is basically the formula for the coefficients that minimize the mean squared error. Okay, so they are optimal in the mean squared error sense. Alpha n is basically this integral, which is the inner product of x of t and phi n of t, scaled by En, which is the energy of basically the function phi n of t. Okay, so this is the solution to our optimization problem. Okay, so to minimize the mean squared error, you need to take x of t and basically find its inner product with each one of the phi's, and you scale by basically the energy of phi n of t, and this will be again the optimal solution. It's meaningless to say just optimal. Optimal in what sense? In the sense of minimizing the mean squared error. And then you can take these optimal alphas and you can plug them in, the formula, the objective function, which is the mean squared error, and get a formula for the minimum mean squared error. And so if you do this, you will find that the minimum mean squared error looks like this. Okay, and so I can write it also as, so the mean squared error is basically this constant term that depends on the energy of x of t, and then we have this extra term, which can be written in terms of the betas like this, or we can write it in terms of the alphas like this. So this can be En alpha n squared, because basically the relationship between alpha and alpha hat is, right? The relationship between alpha and beta is basically this relationship we have here. that alpha n is 1 over en beta n, and beta n is this integral x of t phi n conjugate of t dt. Now, if your functions are real valued, this conjugation will be like redundant, but in the complex Fourier series we use complex valued basically functions, and so it's important like to put to know the general case, and then if your stuff is just real valued, then you can remove the conjugation. Okay, so this is the minimum mean squared error. So this is the minimum mean squared error. Okay, and then what? Then again, like in some sense, this is again a game that is played in data compression, in which I give you like a signal, and basically you want to like compress the signal, and one way of compressing the signal is basically to approximate it as a linear combination of known signals. Those will be the phis, and then the coefficients will be basically what you store, what you process if you are doing processing, and if you want to reconstruct the signal, you can use those coefficients to reconstruct the signal. But here we want more, because we want to reach the Fourier series. We want like to basically investigate the situation when big N increases. So what happens? Okay, so the alphas are unique for mean squared error. Yes, because it's because again because the objective function is a so-called strictly convex function. So you can show that for those, if the objective function is strictly convex, then your minimizer is unique. But if you solve the problem basically minimizing the doing the mean absolute error, for example, like in which like you take the magnitude without squaring, you will get different numbers. And when you do MAE rather than MSE, there are many situations in which the solution actually is not unique. Okay, but in MSE the solution is unique. And for MAE, if you minimize the mean absolute error, in which is the integral of the magnitude without squaring, you will get a different solution. Okay, and actually it may you may have like a family of optimal coefficients in a mean absolute error sense. Okay, but here in our case it is the optimal solutions are unique. Okay, now remember that basically the function that we minimize is something that is guaranteed to be non-negative, right? So we minimize this thing, x of t minus x hat of t squared dt. So this thing by definition, it's the integral of a non-negative function, and so this is greater than or equal to 0. Okay, and so and so basically this thing is its minimum is basically 0, or something that may be strictly positive. But what we can say is that J min, if we use n of those orthogonal functions, is always greater than or equal to 0. So it means that this integral here is always greater than or equal to this summation here. Okay, it's an observation that is not like magical or anything. By the end of the day, it's the function that you are minimizing, the mean squared error, is designed to be a function that is real valued and non-negative, and it cannot go below 0, and its minimum it cannot go below 0. Okay, and so basically the minimum mean squared error will be something that is greater than or equal to 0, indicating that this summation here is upper bounded by the integral of the magnitude squared of the function, which is like the energy of the function from a to b, or its L2 norm squared. Okay, and this is like sort of an important observation. Okay. Okay, so basically, this is our optimal in a mean squared error sense approximation. It is composed of this linear combination of the 5 functions using those coefficients. Again, alpha n hat is 1 over en, integral from a to b, x of t, phi n conjugate of t dt, and this is the thing that I call beta n. Okay. You can compute the energy of the approximation, and it will be basically this second term. So basically the energy of the approximation of x hat is this second term, and so basically we have this inequality. Okay. So we are actually looking at a famous inequality called the Bessel inequality. So let me basically tell you what is going on here. So we have I will actually write it like in the opposite order. So we have summation n from 1 to n magnitude alpha n squared en, and this thing is exactly, you know, magnitude beta n squared over en, again because this is the relationship between alpha and beta. This thing is less than or equal to integral ab x of t squared dt for every n. Again, how did we know this? How did we know this? It's because basically this guy minus this summation is the minimum mean squared error. And the minimum mean squared error is something that is greater than or equal to 0, and its minimum is greater than or equal to 0. So because of this, we know that regardless of our choice of big N, basically this integral is greater than or equal to this guy because their difference is the minimum mean squared error. Now, so this inequality is true for every big N. And if it's true for every big N, what we can do is that we can take limit n tends to infinity of both sides. Okay, so take limit n tends to infinity of both sides. And this will basically be that n from 1 to infinity alpha n squared en is less than or equal to ab x of t squared dt. Note that the right hand side in basically written in black here is independent of big N. So it's like a constant. When you take the limit as big N goes to infinity, this is just a number, which is the energy of x of t on AB. And it's finite, of course, because x of t is L to AB. So it is square integrable from A to B. Now, this inequality again is called the Bessel inequality. And it is true. It is true for any orthogonal family of functions that you use basically to construct an approximation that is optimal in a mean squared error sense. Okay, so keep this inequality in mind. It is useful. Okay. Now, what happens if you, so it's like when I set up the optimization problem, it's like I solved it for a given big N. What happens if you increase big N? So rather than I say, you know, I will use 105 functions to approximate x of t. Now we say, no, I will use 101 or perhaps more. So what will happen? What will happen to the minimum mean squared error? What will happen to the minimum mean squared error? So we are increasing, right? So rather than using n functions, we are using an extra guy here, okay, an extra function. So what do you think? What do you think will happen to the minimum mean squared error? Go to 0? This is like radical, very extreme. Actually, it may go to 0. This may happen, but I want like a statement that is like sort of decrease also, like it may remain constant. It may remain constant. Do you agree? Okay, so if you have an extra function, right? So what do you have? So now if we use phi n plus 1 of t, now we have an extra coefficient alpha n plus 1. Do you agree? Okay, so the optimal guy, so the MSE minimizing coefficient will be what? It has a formula, I mean, because our formulation is general, right? So this thing will be 1 over En plus 1, the energy of the phi function, with the index n plus 1, integral from a to b, then we have x of t, phi n plus 1 conjugate of t dt. Okay, and now Jn plus 1 minimum will be summation n from 1 to big N plus 1 alpha n squared En, and so basically you can then u minimum mean squared, this is with a minus sign plus integral from a to b x of t squared dt. Okay, and so you can write down this minimum mean squared error as, you can split this summation into two terms. So one term will be the new term, and then we will have the sum up to n, and then we have basically a to b x of t squared dt. And what are these two guys together? J min, what is the superscript? This is the minimum mean squared error if you use n, exactly, n, big N functions. Yes, so yeah, so what you get is this thing. Okay, and let me add a hat, right? Because we are, of course, like, we will use the optimal stuff, minimizing our mean squared error. So what are the possibilities? One possibility is that x of t happens to be orthogonal to this phi n plus 1 of t. In that case, this alpha will be 0, and this term will be 0, and the minimum mean squared error will remain the same. It may happen. It may happen that x of t is orthogonal to phi n plus 1. But it may happen that it is not orthogonal. In that case, this guy will be strictly positive, and with a minus sign, basically you will get a reduction. So the two possibilities that we have, that j min n plus 1, it is strictly less than j min of n, and this is if alpha n plus 1 is not equal to 0, right? And then j min of n plus 1 is equal to j min n, and this is if alpha n plus 1 is 0, which means that x of t is orthogonal to phi n plus 1. Now, if it decreases, if the mean square error decreases, will it go to 0? It may happen. It may decrease and go to 0. But again, generally speaking, we don't know. So what we are sure of is that it may remain the same if basically x of t is orthogonal to phi n plus 1 of t. It may decrease to 0 or to some positive value if basically we don't have orthogonality. So by increasing the number of functions that you use in your approximation, right, we are constructing an approximation using n terms. If you increase big N to big N plus 1, you are sure that the minimum mean squared error either remains the same or it is reduced, it gets lower, which sort of makes sense, right? So you are increasing the power of your approximation by saying, I will approximate x of t not by using just big N functions. I will use big N plus 1. I will use more of them. So you may be able to reduce the minimum mean squared error. At least it will remain the same, if you are unlucky enough such that x of t is orthogonal to phi n plus 1 of t. In that case, if you compute alpha n plus 1 hat, the optimal extra coefficient, it will be 0. Okay, so do you agree with this, that phi min n, think of this as a sequence of n as a function of big N is non-increasing? Do you agree? Non-increasing. So if you use just one function in your approximation, you get something. You use 7 functions, you get something that is the same or lower, and so it is non-increasing. Yes, okay. It is non-increasing. Now, it's bounded below. Okay, J min is bounded below. Do you agree? Bounded below. It can never go below some value. Yes, by 0. Exactly. J min of n is greater than or equal to 0. So think of the minimum mean squared error as if it's a sequence in which like big N is 1, 2, 3, 4, 5, 6. As a sequence, it's a monotonically non-increasing sequence. It remains the same or it decays. It gets or it's reduced and it's bounded below. Then so what happens to this sequence? It's monotonically non-increasing and it's bounded below. It can never go below 0. So it converges. Okay, so we know this theorem exactly, this theorem from calculus or real analysis, that basically this sequence, yes, it will converge. Basically the limit as big N goes to infinity, J min of N exists. Okay, it will converge to some limit. Okay, again, something that keeps decreasing. It never increases. It either remains the same or decreases, and it's about, so basically it cannot penetrate the 0 barrier and become negative. So it will always have to stay above 0. Then it should go to some limit. And this limit, based on our discussion till now, is this limit necessarily equal to 0? No, right? It can be something that is strictly positive. So it may basically keep decreasing, and then the limit may be 0.1. Okay? But it is not increasing, it is bounded below, it converges, right? So by increasing n, so now see basically we solved the problem, like in 2 steps. So the first step is like fix big N, find the optimal coefficients. Okay, now we know a formula for the optimal coefficients. Now study the basically if you use the optimal coefficients, now what if you increase big N? So now the conclusion is that we can sustain or reduce the minimum mean squared error, and as n approaches infinity, this will go to some limit that can be some positive number, or like in a good 0 would be nice. Okay, so will the limit go to 0? Yes, if your 5 functions are complete. So that's basically the whole objective of the previous lecture. That basically if your phi's, if you use the sines and cosines, basically you will crush the mean squared error, the minimum mean squared error. It will go to 0 as n goes to infinity. You need completeness, as we will see. Okay, so here, if you wonder, the previous lecture is, then what? Okay, no, it's not, so basically for an arbitrary orthogonal family of functions, the minimum mean square error may go to 0, or it may converge to some positive number. But if you have completeness, that's where you can crush the error, the minimum mean squared error to 0. Okay, so in that case, if the error goes to 0, okay, so in that case, what will happen? So limit n goes to infinity of J min of n is 0. And this is what? What is the minimum mean squared error? It has a formula. It is AB x of t squared dt minus summation n from 1 to big N alpha n squared En. Okay, and so if this limit is 0, this means that the sum n from 1 to infinity alpha n squared En is equal to this. Okay, so remember Bessel inequality. So Bessel inequality, this summation is less than or equal to the energy of x of t on AB, on the interval AB. This is always, for every big N, this is always less than the energy of the signal on AB, and so you can take the limit of both sides and show that basically this infinite sum is always less than or equal to basically this energy. Now, if you are using a family of orthogonal functions that are complete in the sense that they span the L2 space of functions, every function, can be written as a linear combination of these, then basically the limit will be 0 and you get equality. So, welcome Parseval's. That's Parseval's theorem. So we get the very well-known Parseval's relation, which tells you that the energy of the function is equal to this summation that we have here. Okay, and we will compute this summation like for the Fourier series, the trigonometric Fourier series, and for the complex Fourier series. But for now, again, our 5 functions are any orthogonal set. And to have equality rather than inequality. So generally, we have Bessel inequality. This is what we are sure of. If your orthogonal family of functions is complete, like the trigonometric family of functions, then we satisfy the Bessel inequality with equality, and we have Parseval's theorem or Parseval's relation. Okay. Now I need to sort of fill in some details, like how is actually completeness used to show that the minimum mean squared error will converge to 0 rather than to some positive number. Okay, so let's try to think more about this, and so that we can appreciate the proofs of completeness. Why do we like these proofs of completeness? Okay, so suppose that you did the minimum mean squared error game, and you did it till big M, and then suppose that basically Gmin of big N remains constant, right? So basically, suppose that as N here, this is J minimum of N. So suppose that you started using more and more of those 5 functions, you crushed this thing, and then suppose that after some M, this remains a constant. This remains constant. Okay, and again, if it remains constant, constant that is 0, this will be okay, but generally this can be any, it can be some positive. The Gmin of N, the minimum mean squared error may look something like this. Okay. What will make the minimum mean squared error constant? What will make it constant? So let's revisit its formula. So it is a to b x of t squared dt minus summation n from 1 to big N alpha n squared hat En, and this guy here is 1 over En integral a to b x of t phi n conjugate of t dt. What will make this guy remain constant? It remains constant if basically the extra terms that you have in this summation are all 0, right? Because this is something that you cannot control. I mean, basically this is just a constant out there. It's the energy of function x of t. You get reduction in the minimum mean squared error by simply increasing the number of terms that you have in this summation. Now, for the J min n to remain constant, remaining constant means that every extra term that you get is equal to 0, and every extra term is equal to 0. Remember, those energies are strictly positive. So every extra term is 0 if all the extra alphas are 0. So basically, if you are in which the minimum mean squared error becomes flat, becomes horizontal, and it never decays again, it must be the case that x of t is orthogonal to those extra phi functions for every small n greater than or equal to big N. Okay, so this must be 0, which means that the new alphas that you are adding are all zeros, and that's the reason the minimum mean squared error is not decaying anymore, and it remains flat. Okay, so if we are in this situation, it must be the case that x of t is orthogonal to phi n of t for n greater than m. So for n equals m plus 1, big M plus 2, big M plus 3, and so on. So when you compute the alphas, you get zeros. And so basically this term also becomes a constant, and the minimum mean squared error remains constant. Okay. Now investigate the function x of t minus its approximation with m terms, okay, which is this quantity here. Claim that this is orthogonal to phi n of t for every n greater than or equal to m plus 1. Why? Why is this true? Right? So we have x of t. This is true because x of t itself is orthogonal to phi n of t for every n greater than m. If the error remains constant, then this must be true. And so we get the alphas, the extra alphas are zeros, and this will be true. And then we are using an orthogonal family, right? So phi m of t is orthogonal to phi n of t for every m less than or equal to m and n greater than m. Because these two indices are different, and so we are talking about different phi's. So this bracket here, this bracket, is orthogonal to phi n of t for every n that is strictly greater than big M. Okay. Now let's take this bracket, which is the error. It's the difference between x of t. I mean, don't forget what this guy is. This is x hat m of t. This is the approximation using big M terms. Now let's basically take the inner product of this thing with phi j conjugate of t, or phi j of t, and then j is a number from 1 to m. Okay, so this thing you can basically write down as two terms. So the first term is the integral of x of t phi j conjugate of t dt. What is this? This is basically alpha j hat. So this is the optimal coefficient multiplied by EJ. Why? Because basically the optimal coefficient to minimize the mean squared error is exactly this integral divided by the energy of the function phi j. So this integral is alpha j hat EJ. Okay? Now what about when you basically integrate this summation of alpha m phi j of t? You will basically, you can, again, because this for a finite big M, you can interchange the order of summation and integration. You can put the integration inside, and you can now exploit the orthogonality of the phi family. If these two indices are different, you get a 0. If they are the same, and this happens when small m is equal to j, then you will get basically alpha j, you will get alpha, this should be hat, alpha j hat, and then the energy of phi j, and so you get basically this minus this, which is 0. What does this mean? If the minimum mean squared error becomes flat, then we now know that x of t minus its approximation using big M terms is orthogonal to every phi n of t. Again, what I'm doing is the following. I am talking about the scenario, and we are worried that basically the minimum mean squared error will not decay to zero. It will decay to some like constant number that is positive. So let's suppose that it will, after some, if you use big M, basically terms in your approximation, you keep getting a lower and lower minimum mean squared error, and then all of a sudden, the minimum mean squared error remains constant. This constancy means that your extra terms here, as you increase big N beyond big M, are zero, and this means actually that the new alphas are zero, which means that your x of t is orthogonal to basically those extra phi functions. So based on this, so if this scenario happens, it means that x of t is orthogonal to phi n of t for every n greater than big M. And you can extend it to show that x of t minus x m hat of t will be orthogonal to phi n of t, but this is for every small n greater than M. Now, if you investigate this quantity, its inner product with the phi j of t, now with j less than or equal to M, you will find that basically the inner product is alpha j hat ej minus alpha j hat ej. And so this is also equal to zero. And so basically this difference here is orthogonal to every phi n of t. Then what? Then what? Who cares? No, this is basically the previous lecture. If your phi family of functions is complete, remember what was completeness? Actually, what was the idea used in the proof? That if you have a complete set of functions like those trigonometric functions, then if there is a function that is orthogonal to all of them, this function must be equal to zero almost everywhere. Of course, if we are talking about a family of orthogonal functions that is not complete, I cannot make that conclusion. But if those functions are complete in the sense of the previous lecture, then it means that if you find a function, which is this one here, that is orthogonal to every one of them, then it must be the case that this function is equal to zero almost everywhere. So if our basically family of functions is complete, what is g min of M? It is this integral x of t minus x of m hat of t squared dt. Now this thing here, if it's equal to zero almost everywhere, then the integral will give us zero. And so if your functions, the phi's are complete, then and your minimum mean squared error becomes a constant, don't worry, this constant is zero. This constant will be zero, right? Because if your phi functions are complete, then the only signal that is orthogonal to all of them is the signal that is equal to zero almost everywhere. So if our error becomes a constant, and if our phi's are a complete set, then this thing here becomes zero almost everywhere, which means that it's, basically its L2 norm squared is equal to zero. And this means that basically you remain constant, but at zero, okay? And you see why actually this, the business of completeness is important. Okay. Now, again, another technicality, how are we sure that actually this sequence converges? So the sequence, basically, this one. Alpha n phi n of t. So this is a sequence, right? Think of it as a sequence indexed by n. So again, it's like every time you add one extra of those phi functions. Okay, so how do we say that basically this sequence converges? And if it converges, then it converges in what sense? So as you take the limit as n goes to infinity, will this sequence of functions, okay, again, this is a sequence of functions, so the first member here is this one, and then we have this one plus this one, and then we have this one plus this one plus this one, okay, and so you have a sequence of functions, okay, each one with like an extra term relative to the previous one, okay, so this is a sequence of functions. Does it converge? Because if it converges, then this will be, what we call the Fourier series, right? It will be the Fourier series with n going from 1 to infinity, right? But does it converge? Are we know that? And if it converges, so in the previous tutorial session, you learned that, there are several notions of convergence. So is it convergence pointwise? So pointwise means that on AB, on the interval AB, basically the limit of this guy for every t is the limit of this summation here, or it converges in a mean square sense, okay, it converges in a mean square sense, okay, so basically this is the original result. So the claim is that x and t converges in mean square as n goes to infinity. How do we study basically convergence? And if it converges to what? So again, you may know this from a previous course on calculus or real analysis, that if you want to investigate the convergence of a sequence and you have no idea about the limit, what can be the limit, you can do so by studying basically something called the Cauchy sequences. Okay, so basically what we can do is that we will study the L2 norm squared of the difference between xn of m and xm of t. Okay, so so basically this is one of those, one member in the sequence and another member in the sequence. And we measure basically the L2 norm squared. Now, basically this is a summation in which you go from 1 to n. This is a summation in which you go from 1 to big M, and you are taking the difference. So basically the difference will go from the minimum plus 1 to the maximum, right? So if you have two indices, one going from 1 to 10 and one going from 1 to 20, right? Then basically you are going from 11 to 20, right? So you will go from the minimum plus 1 to the maximum. And so you get basically this summation. You can extend this summation. You can take the magnitude squared, and then you can do the integration first to get basically this summation here. And so it's a summation from the minimum plus 1 to the maximum, and we are summing non-negative terms. And so this is always less than or equal to if we start from the minimum plus 1 and then go all the way to infinity. Okay, so this is an upper bound. This is an upper bound. Now, what is the limit n goes to infinity, m goes to infinity of this summation L from minimum nm plus 1 to infinity alpha L squared EL? What is basically this limit of the upper bound? Now remember that basically summation L from 1 to infinity alpha L squared EL, this summation is upper bounded by Bessel inequality by integral a to b x of t squared dt. So this is Bessel. And this is finite because we are talking about square integrable functions. So this summation converges if you take it from 1 to infinity. So what if you start this summation from some index and then take the limit as this index goes to infinity? So there is again a result in calculus or real analysis that basically if you have a convergent series, if you start from an index to infinity and you take the limit of this lower index going to infinity, this limit will be zero. This limit will be zero. And so basically the limit of this thing here by the squeeze or the sandwich theorem, because this thing is greater than or equal to zero, this will be zero. Now you look at this thing and say, what does it mean that, you know, you take basically x of nt, take the difference magnitude squared, you integrate, and then you take the limit, and this is zero. This means that our sequence is a Cauchy sequence. Okay, so hopefully at least some of you know this from some previous life. Now Cauchy sequences converge in complete spaces. Okay, so this is now getting messy because now complete here is used in a different sense. So we say that the L2AB space is complete. We say that a space is complete if in that space every Cauchy sequence converges, is guaranteed to converge. Now if you have no idea what Cauchy sequences are, you can skip this part and just take it for granted. Okay, if you know this, then you know, I mean, you know, how do we know that actually this sequence converges? Okay, so again, it is because we don't know a candidate limit. We in complete spaces we study limits via Cauchy sequences, and complete here is used in a different sense than from the previous lecture. In the previous lecture, by complete, I meant an adjective that is basically used to describe a family of functions that basically a family that spans the space of possible functions. Here by complete, it's meant that it is a space in which every Cauchy sequence converges. Now why basically people use the exact same adjective to describe two different things? Well, I mean, it's definitely it's not me who came up with these basically descriptions. Okay, yeah, I mean, it's a problem actually in the area that sometimes there are terms that are overused, so they are used like to mean different things. Okay, if you are not in the business of Cauchy sequences, that's okay. Just take it for granted that basically x of n of t converges in mean square. You can show rigorously that it converges in mean square. This thing here will converge in mean square. And by convergence in mean square, I mean the following. So this is what is important. So you can basically skip everything I said like in the last 5 minutes and say, you know, that there exists a function that is L2AB such that this is equal to 0. So this sequence here, so this guy is summation n from 1 to big N alpha n phi n of t, and there exists some L2AB function such that if you take the difference square and then take the integral from a to b dt, this will be 0. Okay, this thing will be 0. Okay, so this limit exists, and it's a limit in a mean square sense, not pointwise. Okay, and this is important like to understand when we write the Fourier series, what actually we are talking about. So, you know, according to what I'm doing in this lecture, we are talking about something mean square convergence, not pointwise convergence. Okay, and so there is, you know, basically the last part of this like sort of abstract story about the Fourier series we will finish at the beginning of the next lecture. Okay, so for now I'll try to basically tell the story of the Fourier series as if we are doing approximation to a certain function, using some known family of orthogonal functions. And so we take an x of t, we try to approximate it as a linear combination of some phi functions that are orthogonal to one another. And we basically obtain the coefficients by minimizing the mean squared error. And then we ask ourselves the question, what if we use a large number of these phi functions? Will we be able to reduce the mean squared error to 0? We can do so if our family of functions is complete